Hello again. This is lecture 14, part 2. In the previous video, we considered examples when the characteristic equation of the differential equation has distinct roots. And in this video, we will see what to do when we have, okay, so this is, we can take this to be case 2. We have repeated roots. Okay, so I'm only going to consider the case when the characteristic equation is of the form lambda minus some number lambda 0 to the power n. So that lambda equals lambda 0 is a root with multiplicity n. Remember what this means when we convert the differential equation into a system, dx dt equals ax. It's homogeneous, we consider homogeneous equations still. So in this system, the matrix A has eigenvalue lambda 0 with multiplicity n. Remember, in this case, the Jordan form of the matrix A is, what is the Jordan form? Remember, when we consider systems. So in the Jordan form, we have the same number on the diagonal. And in the minor diagonal, in the diagonal above the main diagonal, we have ones and other entries are 0. And when we take matrix exponential of this Jordan matrix, on the diagonal, we have the same function, e to the lambda 0 t. But because of these ones, we obtain some non-zero entries above the main diagonal. And what are those entries? In all of the entries, we have, again, the exponential function, e to the lambda 0 t, but then it is multiplied by powers of t. So the next one, when we consider the first row, the next entry is t times e to the lambda 0 t, and then t squared over 2 times e to the lambda 0 t. And the last one is t to the power n minus 1 t to the power n minus 1 divided by n minus 1 factorial times e to the lambda 0 t. This means, so for the fundamental matrix, remember, we multiply the matrix exponential with a special matrix P, but the matrix P is going to be a constant matrix. So first components of the solutions of the system are some multiple when we look at the first component, it means we look at the first row of the matrix exponential. And in the first row, we have n independent functions. And the first components, in each component, we are going to have one of those functions. So what are the functions? E to the lambda 0 t, t times e to the lambda 0 t, t squared times e to the lambda 0 t. It is true that in the first row of the matrix exponential, we have t squared over 2, but the number 1/2 is just a constant. So since I'm considering multiples of the functions, I don't need to take the constant 1/2 into account. And the last one, t to the n minus 1 times e to the lambda 0 t. So we have n functions again, because we have an n by n system. And those n functions gives us, okay, the system is n by n. That means the original differential equation has order n. And here are the n independent solutions of the equation. So in this case, the general solution, in this case, the functions e to the lambda 0 t, t e to the lambda 0 t, up to t to the m minus 1 e to the lambda 0 t, gives n independent solutions of the differential equation. Okay, so let's consider some examples. In the first example, let's consider the equation. And again, let's take an initial value problem. So solve the initial value problem. Second derivative of y minus 2 times the first derivative of y plus y equal to 0. And the initial conditions are y0 equals 1 and y prime 0 equals minus 1. Okay, so first we need to obtain the general solution, and using the initial conditions, we are going to figure out the constants. So to find the general solution, we consider the characteristic equation. It is lambda squared minus 2 lambda plus 1 equal to 0. Remember how we write the characteristic equation? We just take the coefficients of in the differential equation. Okay, so lambda squared minus 2 lambda plus 1 is lambda minus 1 squared. And when we set this equal to 0, we have lambda equals 1 as a double root. So that means the functions, the first solution, taking the value lambda equals 1 is e to the t. And the second one, since it's a double root, we multiply e to the t with t. And this is where we stop. It's a double root. The equation is second order. We need only two independent solutions. So these two are the independent solutions. So that means the general solution is of the form constant C1 times e to the t plus constant C2 times t e to the t. Now, to find the constants, we use the given initial values. First, y0 equals 1 means in the general solution, we substitute 1 for y and 0 for t. So if you substitute 0 for t, e to the 0 is 1. And in the next term, t is 0, so next term vanishes. So that means the first constant, C1, is 1. Now, to use the second initial condition, first we need to find the derivative of y. We find the derivative, of course, from the general form of the solution. We already know that C1 is 1, so we have just e to the t. When we take the derivative of e to the t is, again, e to the t. Plus C2 is constant. We need to differentiate t times e to the t. We use product formula. Derivative of t is 1 times e to the t plus t times derivative of e to the t is, again, e to the t. And now we use the initial condition. Y prime 0 is minus 1. So for the derivative of y, we substitute minus 1. And for t, we substitute 0. So e to the 0 is 1. Oops. Yes. E to the 0 is 1 plus C2 times e to the 0 is 1 and t is 0. So t e to the t is 0. So we have just C2. That means the constant C2 is minus 2. So the solution we are looking for, C1 is 1, so e to the t, and C2 is minus 2 times t e to the t. This is the solution we are looking for, solution of the initial value problem. Now, in the next example, so this is what we do if a real root is a double root, but it is possible to have a complex root as a double root. Again, we are going to follow the same thing. For the double root or triple root or whatever root with multiplicity more than 1, we keep multiplying with powers of t until we get the number of necessary solutions. Okay, so as the next example, let's solve the equation. The fourth derivative of y plus 6 times the second derivative of y plus 9y equal to 0. So here, this is 9. Looks like an A, 9. Okay. So this is not an initial value problem. We are going to give the general solution. We write the characteristic equation. Y to the 4 corresponds to lambda to the 4 plus 6 times second derivative of y corresponds to lambda squared, and 9 times, when you have just y, we don't take anything. So y, when you have y, you can consider this as the 0th derivative. We are not taking any derivatives yet. So when we don't take any derivative, we don't have a lambda. It's the constant term. So the constant term is 9. equal to 0. Oops. Okay, so we can factor this out. This is just the square of lambda squared plus 3, right? Lambda to the 4 plus 6 lambda squared plus 9. So we have lambda squared plus 3 equals 0. So lambda squared equals minus 3. That means lambda is plus or minus I times square root of 3. So we have two complex roots, but they are double roots. So I times root 3 and lambda 2, which is minus I times root 3. So this is the conjugate of lambda 1, are double roots. So when we have the complex root, remember, we don't need to consider the conjugate. We get all the information we need from one complex root. So lambda 1, I take lambda 1, I times root 3. So the number A is 0, and number B is square root of 3. So e to the at is going to be e to the 0, which is 1. So corresponding solutions, y1 is going to be cosine of square root of 3t, and y2 sine of square root of 3t. These are the solutions we get from the complex root I times root 3. But remember, it is a double root. Since it's a double root, since I times root 3 is a double root, we have the third solution. We multiply the first solution by t. T times cosine root 3t. And y4, I multiply the second solution, y2, with t. Are also solutions. So in this way, we get 4 independent solutions. That means the general solution C1 times cosine of root 3t plus C2 times sine of root 3t plus C3 times t cosine root 3t plus C4 t sine of root 3t. So when a complex root is a double root, and why is a double root? Because this is a double root because of this square. We are taking lambda squared plus 3 squared. So each solution of lambda squared plus 3 equal to 0 is going to be a double root. So when we have a double root, when we have a complex root, which is a double root, we write the solutions corresponding to the complex number lambda, and then since it's a double root, we multiply each solution with t to get the other solutions. Now, of course, a double root may be combined with a single root. For the double root, we apply this procedure of multiplying by powers of t, and for the single root, we just take the corresponding solution. So as another example, let's solve the equation. The third derivative of y minus 3 times the second derivative of y equal to 0. So again, first we write the characteristic equation. So third derivative of y corresponds to lambda cube minus 3 times second derivative of y corresponds to lambda. So this is equal to 0. Now, in this polynomial, lambda squared is a common factor. So if you factor out lambda squared, we have lambda minus 3. So from lambda squared equals 0, we get the solution lambda 1 equals 0, but this is a double root. And then from the other factor, we have lambda 2 equals 3. All right, now from lambda 1 equals 0, we get the first solution, e to the 0 times t, so that's e to the 0, which is 1. So the constant function 1 is a solution. Okay? I mean, you can easily see that any constant is a solution, because remember, once you have a solution, any non-zero multiple of it is also a solution. So when you take y, the function y, to be a constant, any constant, you see that it satisfies the equation because the derivative is 0, so second derivative is 0, third derivative is 0, the equation is satisfied. So any constant is a solution. So as the independent solution, we take the constant 1. Now, but this is a double root. Lambda 1 equals 0 is a double root. So the second solution we get by multiplying the first solution by t. So t times the first solution, let me say. So my second solution is t. Okay. Now I have another root, lambda 2 equals 3. So this gives me my third solution. My third solution is e to the power 3t. So my general solution y equals c1 times 1. So just c1 plus c2 times t plus c3 times e to the power 3t. So in this example, oops, okay. So in this example, we see, I guess this is the first example when we have 0 as a root. So if lambda equals 0 is a root of the characteristic equation, then y equals 1, and consequently y equals c are solutions for any c. Okay, so for lambda equals 0, and the reason is, as we did here, when you have 0 as a root, the corresponding function you consider e to the power 0 times t, but that gives you the constant 1. And you can multiply it with any constant, you still get a solution. So in this case, when y equals 1 is a solution, then y equals any constant is also a solution. And when you have a double root combined with a single root, for the double root, you write the first solution plus t times the first solution. And if it's the triple root, you keep multiplying with powers of 3, and you add the function for the single root. So this is all the examples I'm going to consider for homogeneous linear equations with constant coefficients. Next, we are going to consider non-homogeneous. And we are going to, remember for systems, we considered non-homogeneous systems and used the method of variation of variables, variation of parameters, I'm sorry. For a differential equation, nth order differential equation, we are going to consider another method for non-homogeneous equations when the function on the other side of the equation is of a special form. So that's coming up next. And that's all for this video.